Hello everyone. This is the webinar on work and energy for year 10. I have done this webinar before, so you can always go back and watch my previous year's webinars. So the main ideas that I will be talking about today is, well, work and energy, obviously. What is work and how it is related to energy? I won't be talking about all forms of energy. You should know of at least kinetic energy, gravitational potential energy, elastic potential energy by now. You've probably heard of chemical, nuclear, and all sorts of energy. We'll be focusing mostly on kinetic, gravitational, and elastic energy today. So, what to understand energy, you first need to understand work. Work is well, the definition. Work is force times distance. Except not quite force and distance, because um, it also depends on which way the force is and which way the distance is, which way you're moving. So that's your school definition. That's your school definition. We'll have a slightly better one. Work is force times distance times cosine of the angle between force and distance. But you will say, well, distance is not a vector. Force is a vector, yes, but distance is not a vector. So let's remove that word and say displacement. Displacement. Now, displacement is a vector. And now, so imagine you're moving a box and you're applying a force. You're pulling the box this way, and the box is moving that way. So that's your force, and that's your displacement, S. S is the displacement, and F is the force, and theta is the angle between the two. And in this case, so the work done is force times displacement times the cosine of the angle between them. Okay, that's the first thing. So when you apply force, and that's something that you're pushing moves, that means you're doing work. You can imagine if you're pushing a heavy, well, if you're pushing a car, for example, the car is stationary, you push the car starts moving. So you're doing work on the car. As you do work on the car gains kinetic energy. Well, yes, if you push and the car moves, that means the car acquires kinetic energy. And that comes to our very important work energy principle. Work energy principle. And it looks like this. The change in kinetic energy of an object is equal to the total work done on that object. Let that sink in. If I take a golf ball, this is not a golf ball, but close enough. And if I apply a force to that ball, and the ball, as a result of that force, the ball moves, the ball will have kinetic energy equal to the amount of work I've done. And that's very important. And it's not an obvious thing. Example. Let me just take a quick picture of myself. All right. So if I do 3 joules of work on the ball, the ball gains 3 joules of kinetic energy, assuming that no other force has done work on the ball, right? Because if gravity does work on the ball, gravity can do work on the ball, that means the ball will gain more or less. It depends. All right. But the idea is that if I do 3 joules of work on the ball gains 3 joules of kinetic energy. And that's your work energy principle. So change in kinetic energy, once again, is equal to the work done. Okay. Slightly confusing. It's the total work done. Work done on the object. Because you will ask me, well, what happens if I take this ball and I move it to the top shelf? The ball hasn't gained any kinetic energy, has it? Its kinetic energy is still 0. So what happened? Well, as I was doing the work on the ball, so was gravity. I was speeding the ball up, but gravity was slowing it down, as well as friction, of course. And eventually, the total work on the ball is 0. So the combined work by me, by gravity, and by friction is 0. Does that make sense? On a scale of 0 to 10, please tell me in the chat. No Q&A today, just a chat. No? Anyone? 10, okay. So example 2. Example 2. If I move the ball to the top shelf, the change in kinetic energy is 0 because the ball was not moving initially and it's not moving now, which means that the total work, which is equal to the work done by Vlad plus the work done by gravity plus the work done by friction, is 0. Okay, I hope that makes sense. And yeah, quick example. Fet forces and motion. And if so this is a box, and if I push the box and the box moves, you can see that the speed of the box increases. So I'm doing work because I'm pushing the box and the box is moving and the kinetic energy of the box is increasing. If I stop pushing, the kinetic energy of the box does not change because I'm not doing any work on the box. I'm not inputting any energy into the box. If I push the other way, I'm removing energy from the box, which means I'm doing negative work. How does that work? How does that work? How does it make sense? The box is moving to the right. So the displacement is to the right. Let's say the box moves 30 meters. And I'm pushing to the left 50 newtons. And the angle between the force is 180 degrees. So the work is force times displacement times cosine 180 degrees. And force is 50 newtons. times 30 times cosine 180, which is minus negative 1. So negative 1,500 joules. So if I'm pushing in the opposite direction, is work the same as transfer of energy? Work is a method of transfer of energy. Yes, mechanical. You've studied that in GCSE. Mechanical transfer. That's work. That's literally what it is. It's a transfer of energy. So work is minus 1,500 joules. That means the box loses 1,500 joules of kinetic energy. That's very important to link those two. And in an exam, you would always be asked, what is the work done by that force? And then what is the change in kinetic energy? And it will be a 1 mark question. You need to realize, well, it's the same thing. Okay, so we have introduced the concept. Work and energy are both measured in joules. And a very so work and energy measured in joules. Sometimes in calories. So if you're doing chemistry, or sometimes calories, and 1 calorie is 4.2 joules. It's the energy needed to heat up 1 milliliter of water by 1 degree Celsius. Energy needed to heat 1 gram of water, which is the same as 1 milliliter, not always, by 1 degree Celsius. Now, if you're into nutrition or any kind of nutritional value, you will sometimes hear that a person needs 2,000 calories per day. That is not true, because they are confusing calories and kilocalories. So a person needs about 2,000, not calories, but kilocalories. And so somehow they forget the word kilo. So they're off by a factor of 1,000 kilocalories, which is approximately 8.4 times 10 to the 6 joules, as far as I understand. Yeah, of from food per day. So quite a lot, right? So yes, and 1 joule. To understand what 1 joule is, just to get a very simple understanding, if you take an apple and you lift it by 1 meter off the ground, so you lift it by 1 meter, the amount of work is approximately 1 joule. 1 joule is the work required to lift an apple by 1 meter. So you could imagine that 2,000 calories, 2,000 calories is just what 8,000 joules, which is nowhere near enough what you need to consume per day. Anyways, let's move on to problem 1. A 12-kilogram box is pulled along a horizontal surface by a force 60 newtons acting 25 degrees above the horizontal. The box moves 15 meters. Okay, so we have a box and we are pulling using a rope, and the force is 60 newtons, and it is acting at 25 degrees. The box moves 15 meters, so the displacement of the box is 15 meters. 15 meters. And the friction force is 18 newtons. Find the work done by the pulling force. So A, work by the pulling force. Well, it's equal to force times displacement times cosine theta. In this case, it is 60 times 15 times cosine 25, which is approximately 60 times 15 times cos 25 degrees, 816 joules. Work done by the friction. Work done by friction. Now the friction, the displacement is to the right and the friction is to the left, so the angle between the displacement and friction is 180 degrees. So Fs cos theta, theta 2, well, this is theta 1, and this is theta 2. So it's 18 times 15 times cos 180 degrees. So it's 18 times 15 times -1, so negative 270 joules. The total work done. See, total. Now, before I calculate the total work done, we also need the work done by the normal force, because there are two more forces, and the work done by gravity, right? Now the gravitational force is down, force of gravity. And the normal reaction force is from the ground, F normal. But in both cases, the angle is 90 degrees, right? If you think about it, if you see the gravitational force and the displacement S and gravitational is 90 degrees. So as the box moves, work done by gravity is equal to force of gravity, which we don't necessarily know, times the displacement times cosine 90 degrees. But cosine 90 degrees is 0, therefore the gravity does 0 joules of work. And work done by the normal force, similar scenario. The normal force times S times cosine 90 degrees equals 0 joules, because that's 0 degrees, 0, 0 as well. Okay, now a question for you. If, look at this scenario, if the gravitational force was 100 newtons, would the normal force also be 100 newtons? Yes or no? In the chat, please. If the gravitational force is 100, would the normal force be 100 as well? Don't worry. Don't be afraid to get it wrong. And don't be afraid to get it right. So No, yes, yes. So quite a few people are saying yes. Can you argue your no? Ah, well, it was a correct guess. It would be not be the same. The reason for that is because that force you're pulling up. So you're all sort of lifting the box off the ground. So you're reducing the normal force. So if you look at this situation, there's the gravitational force of 100. There's a normal force here, normal force, and there's the pulling force, which has two components. It has a component horizontally, but also a component up. So if this is F cos theta, and this is F sine theta. And you can see that these two together make 100. So n plus F sine theta is 100, and therefore n is 100 minus F sine theta, and that which is less than 100 newtons. So the normal force, well, it's a sort of a simple thing. If you're trying to lift something off the ground, the normal force reduces, right? So you're kind of helping the ground. Okay, but let's get back to our question, because the work done by the other two forces is zero. They're not doing any work, and that's important to understand. So the total work is the work done by the pulling force, plus the work done by friction, plus the work done by gravity, plus the work done by the normal force. And this is 816 minus 270 plus 0, which is minus 816, 546 joules. That's the total work done. The final speed of the box. Oh, it's a 12 kilogram box. So it's 120 newtons. Well, anyways. Hundred and twenty newtons. 20, 20 newtons. Okay. So the final speed of the box, if it starts from rest. So here we use the work energy principle. Work energy principle. So the change in kinetic energy of the box is equal to the work done. Work. So 1/2 mv squared, that's the kinetic energy, is going to be 546. So m is 12. M is 12, so 6v squared equals 546 divided by 6, 91. So v squared is 91. V is approximately 9.9.5 meters per second. That's the speed of the box. Lovely. A cyclist of mass 80 kilograms is moving at 8 meters a second. So we have a cyclist. I obviously can't draw a bicycle. Okay. Nor can I draw a cyclist. Okay. 70 kilograms together with the bike, I assume. So moving at 8 meters a second, coming to rest over a distance of 20 meters. So it travels 20 meters before coming to rest. 20 meters. Okay. And the work done by friction. Well, first of all, we need to find the change in kinetic energy. The change in kinetic energy is the kinetic energy final minus kinetic energy initial. Final kinetic energy is 0 minus the initial kinetic energy is 1/2 mv squared. That's the formula. So 0 minus 1/2 times 70 times 8 squared. 70 times 32. 70 times 32. Negative 240 joules. So the change in kinetic energy is negative. It is negative. So the work is the change in kinetic energy, which is equal to negative 240 joules. Well, assuming that's the only force that's doing the work, because we know gravity doesn't do any work when you're moving horizontally, because gravity is down and you're moving that way, so there's 90-degree angle. The normal force doesn't do any work either, because it's up and you're moving to the side. The friction does work, and assuming that the cyclist is not pedaling, because if the cyclist is pedaling, obviously they do work and the friction does work. So the friction, the work done by friction would be more. You would need to remove more energy from the system if you keep inputting the energy into the system. Right, so the work is in minus 2240. And yes, the frictional force, B. So work, we know, is the force times distance times cosine theta. And we know that cosine theta is 180. So it's the force times 20 times cos 180, which is negative 1. And that's equal to minus 2240 joules. And therefore, F is equal to minus 2240 divided by negative 20. Divided by 20, which is 112 newtons, the frictional force. And the coefficient of friction. Ooh, that's a nice question. So assuming the horizontal road and the cyclist is skidding, and the cyclist is skidding. So this is when you press the brake so hard that you slide along the road. Right, so that is so this is the cyclist. And so the frictional force I won't let you know, Kevin. So friction I'll explain. So the frictional force is backwards, obviously. This is the normal force. This is the gravitational force, mg. So normal force must equal to mg because nothing's pushing the bike up or down. Normal force is mg. And the frictional force is equal to mu n only if it's dynamic friction. Dynamic friction. With no slipping, the frictional force is less than or equal to mu n. So we don't really know the force of friction. Well, we don't really know the coefficient of friction in that case. So the skidding matters because only then we can be sure that the frictional force is mu n. Otherwise, it's just less than or equal to mu n, which is not good enough for us. And therefore, but n is mg, so the frictional force is mu mg, and we know that the frictional force is 112 equals mu times 70 times 10. So mu is 112 over 700, which is approximately 700, 0.16. So that's a very snowy conditions, probably very muddy, very muddy. Because on a dry road, you would expect at least 0.8 on a dry road. Mu is approximately, well, it's greater or similar to 0.8. Okay, so that's the coefficient of friction for you. Coefficient of friction tells you the fraction of your weight, right? So if coefficient of friction is 0.5, that means the frictional force can be up to half of your weight. Okay. Problem 3. Stuff down. A ball is dropped from a height of 2 meters. Each time it hits the ground, it loses 30% of its kinetic energy. Find the height reached after the first bounce. Well, when the ball is at the top, it falls down. It bounces back up. Hits the ground. So at the top, it has gravitational potential energy at height h0. At the top, gravitational potential energy is mgh. And as you're dropping, this converts to your kinetic energy. Kinetic energy at the bottom. At the bottom, you have kinetic energy, which is equal to your mgh0. After bounce, kinetic energy is equal to 0.3 mgh 0 or 0.7. Sorry, it loses 30%. So it's 0.3, 0.7. Right. So here we have mgh0, gravitational potential energy. Here we have mgh1, mgh2, mgh3. When you drop a ball from the top to the ground, it will have kinetic energy exactly, well, equal to the gravitational potential energy it had before. So the kinetic energy it has is mgh0. But once it bounces, it goes mgh1 up. So when it bounces back up, it has mgh1 energy, where h1 is the height reached after the first bounce. And that means if you lose 30% of your energy, That means by the time you reach the first bounce, you will have 70% of your original gravitational potential energy. Okay, so I hope that makes sense. That means mgh1 is 0.7 mgh0, and therefore h1 is 0.7 h0. And if it's dropped from a height of 2 meters, the height reached after the first bounce is h0 times 0.7, which is 1.4 meters. Just as simple as that. The height of the second bounce is h1 times 0.7, which is, I assume, is 0.98 meters. 1.4 times 0.7. Yep, 0.98 meters. How many bounces will it bounce to less than 0.5 meters? Well, this is a geometric sequence. So A 0.98 meters, and first bounce, second, third, yeah. So C, we have 1.4. The first bounce is 1.4. The second bounce, would you not say that kinetic energy to first bounce is GP initial? Yes, that's what I'm trying to say, which is GPE initial. Oh no, because it loses when it hits the ground. Some of the energy goes into heat, right? Some of the energy goes to thermal energy. Yeah, 1/2 mv squared. But we don't need speed. Okay, we're not looking for speed. So the height of the bounces, so 0.98, etc. So this is a geometric sequence, and we know that in a geometric sequence, UN, the height of the nth bounce, is the height of the first bounce, so h1, multiplied by the common ratio r to the power of n minus 1. So the height of the nth bounce is the height of the first bounce times 0.7 to the power n minus 1. And that is less than 0.5. So 0.7 n minus 1 is less than 0.5 over 1.4 over 1.4, which is 0.35714. So n minus 1 is less than the logarithm of 0.35714 or 0.7, which is a change of sign because the base is less than 1. And the logarithm 0.7 of ounce is n minus 1 is greater than 2.887. So n is greater than 3.887. So n is 4. N is 4. So for the fourth bounce, after 4 bounces. Okay. Hi, what time is it? 6:40. Oh, nice. A mass of 3 kilograms slides down a smooth incline from a height of 4 meters and travels along a rough horizontal surface with coefficient of friction of 0.2. So we have a smooth incline, an object 3 kilograms, height of 4 meters. Then travels a rough horizontal surface. So when it reaches, it's a rough surface. And the coefficient of friction is 0.2, not that rough. How far it travels along the rough surface before stopping. Okay. So as it goes down, it gains energy, and it's actually work done by gravity. Work done by gravity is mgh, because it's moving down, and it's equal to mass, which is 3 times 10 times h, which is 4. Okay, it's quite easy to prove. So that the work done by gravity is mgh. I won't do it today because I've done it before, but it's important. It's either mgh or minus mgh. H, if you're moving, work done by gravity is positive if you're falling, and the work done by gravity is negative if you are rising. So if you're going up a hill, gravity is doing negative work. It slows you down. Yeah, gravity slows you down if you're crawling up a hill. And if you're rolling down a hill, gravity is your friend. Well, hopefully. Does the gradient? No, the gradient doesn't matter. That's the thing that I need to prove. So I'm not too keen on doing it now, but the gradient does not matter. Only the height matters. Um, The kinetic energy at the end would be the same. Uh, and the gradient slope is irrelevant. Okay, now I want to prove it. Okay, I will prove it. So imagine the slope is theta. Then the distance traveled, the distance traveled is 4 meters. Well, the height uh, divided by sine theta. I divided by sine theta. Now, the force of gravity is mg, and the force is down, and you're moving this way. So this is s, and this is force of gravity, which is mg. And you need this angle, and this angle is pi over 2 minus theta. So work done by gravity is the force of gravity mg represents the weight and h represents distance. Yes, that is correct. Mgh cos theta, mgh. Yeah, but what's cos? Oh, cos 0. Yeah, you can think of it that way, of course. Gravitational force times the distance times the cosine of the angle between them. Cosine, and the angle is, sorry, not pi. Let's grab pi over 290. And 90 minus theta. Cos 90 minus theta. And this is the angle between mg and s. And then the force of gravity is mg, and s is h over sine theta. And then times cos 90 minus theta, but cos 90 minus theta is actually sine theta times sine theta. And sine theta cancels, and you get mgh. So the work done by gravity is mgh, and the slope does not matter. It's only the difference between the final height and the initial and final height, which is very neat. If theta is just less than 90, if theta is just less than 90. Theta is close to 90. Well, if theta is close to 90, it would hit the ground vertically. And it will lose energy from the hit. And if it doesn't lose energy, it will bounce. It will bounce up and down. And yes, it won't travel horizontally because it's using that energy to bounce up and down. Here, we assume that there's no bouncing and all the energy goes into the lateral motion, to the sideways motion. So if that makes sense. It's a good point, yes. Uh, in these questions, we always assume that at the end, there's a smooth transition from the slope to the ground, so that eliminates the bouncing, if that makes sense. So no bouncing, no bouncing. So in your extreme case scenario that you're describing, thank you for that. I was never thinking like that. So extreme case scenario when theta is approximately 90, theta is approximately 90. The ball hits the ground, but yeah, there's still like a mini tiny little transition here, which doesn't allow the ball to bounce. It actually the ball just goes horizontally, like a like vertical slides. Uh, I still really enjoy them, honestly. The slide that goes vertically down and then goes sideways. Uh, so yeah. So where was I? Yes, the work done by gravity is 3 times 10 times 4. So that's what 30 times 4, that's 120 joules. And that's the kinetic energy that you have. Kinetic energy when that you have at the bottom. Kinetic energy is 120 joules. And then friction takes that energy away. Friction needs to remove. Friction needs to remove 120 joules of kinetic energy. And that means that the work done by friction is negative 120 joules. And what is friction? Well, we know that friction is mu n when it's sliding, mu n, which is equal to mu mg. Mu mg. This is mg. This is the normal force. Once again, so this is the friction force. This is the normal force, and this is the mg. They're the same, mg. So n is mg, and this is mu n, which is mu mg. So under normal circumstances, if you're sliding along the ground, the frictional force is mu mg. It's a very good thing to remember, mu mg. And therefore, mu mg is negative 120 joules. Sorry, that's the force times the distance, s, and times cosine 180 degrees. Remember, cosine 180 is negative 1. So that makes it plus, and S is equal to 120 joules divided by mu mg. So 120 divided by 0.2 times 3 times 10, which is 36. So 120 divided by 6. Divided by 6 is 20. 20 meters. And that's the answer. Right. Problem 5. A spring with spring constant to 400 newton meters is compressed by and used to launch along a horizontal frictionless surface. So the energy stored in a spring, so you have a spring, and this is an object. The spring is compressed. So it was initially like this, and then it was compressed by 0.2 meters, and this coefficient spring's constant is 400 newtons per meter, and used to launch at 0.5 kilograms, so the mass is 0.5 kilograms along a frictionless surface. So when you release the spring, the object travels with a speed v, which we need to find. And so the energy stored in a spring, so A, elastic potential energy is 1/2 K delta X squared. So it's 1/2 times K, which is 400, times delta X, which is 0.2 squared. And that is 0.5 times 400 times 0.2 squared, which is 8 joules. That's the energy stored in the spring. Elastic potential energy. The speed the object has, so elastic potential energy is converted into kinetic energy. And therefore, a half mv squared must equal to of k delta x squared. And that's equal to 8 joules. So mv squared is 16, and v is equal to square root of the energy divided by 2m, which is square root of 8 over 16 over, wait, 2e over m, sorry. Equals 2e over m. Okay, 1/2 mv squared is equal to energy, 2 energy over m, so that's 16 over mass, which is 0.5, which is square root of 32, which is 4 root 2, square root of 32, which is 5.7 meters per second. Why is elastic potential energy 1/2 K delta X? I've covered that in one of my previous webinars, but if you compress a spring, if you apply a force F, then the force is Kx. It's and if you draw a graph of displacement versus force, you will see that the force increases with the further you move, the bigger the force is. But the work is force times distance, right? So you can split that into tiny little. Just a second. You can split that into tiny little sections, and in each section, the force times the small distance, delta x, so F times delta x. So in other words, the work done is the area under the graph. Work is the area. Force times distance. Force times distance. But the force keeps increasing, and that's equal to 1/2 force times delta x. Delta x is this value, is the extension, delta x. But, so the work is the area of this triangle. So work is area, which is 1/2 times F, which is the final force, times delta x, which is the total extension. And then, but if area is this, and F is k delta x, and therefore we substitute that into here, which is 1/2 k delta x, which is 1/2 k delta x squared. I hope that answers your question. Moving on. A car engine delivers a power of 50 kilowatts and moves the car at a constant speed of 25 meters per second. So let's talk a little about power. Power is work divided by time. But work is force times displacement divided by time. But if you do force times displacement over time, displacement over time, that's velocity. So that's force times velocity. So in other words, power can be written as energy, well, work divided by time. It can also be written as energy divided by time. It also can be written as force times velocity, force times speed. A car engine delivers a power and moves the car at constant speed. Well, I love this question. It's a really nice one. Because what happens is the speed is constant. The speed is constant. That means that the change in kinetic energy is 0. Speed. Therefore, change in kinetic energy is 0. That means that the work done is 0. But you need to understand that it's the total work. It's the work done by the engine plus the work done by the friction. Total. That the work done by the engine plus the work done by the friction is 0. By the resistive force, we mean, well, yeah, the frictional forces, the air resistance and friction. In other words, work done by the engine must equal to minus the work done by the friction. And it makes sense because the work done by friction is negative. So work done by the engine is positive. Okay. But that also means that the power of the engine must equal to minus the power of the friction force. And that means that the power of the engine, or also that means that the force of the engine must exactly equal minus the force of the friction. Oh, that's nice. That's a nice realization. In order to move at constant speed, the force that pushing you the force that is pushing you forward must exactly equal the force pushing you backwards. Well, yeah, I think that's what I've been telling you for the last several months, trying to convince you that this is true. And this is very obvious from this in this situation. Look, if I push, um, if I push with uh, 92 newtons, and the frictional force is 92 newtons, the speed does not change. So in order to move at constant speed, my force must exactly equal to the frictional force. If I want to go faster, I increase the force, and that speeds me up. But if I go back down to 92, I remain at constant speed. It is because of net force, yes. It is net forces here. So the power of the engine is the force of the engine times the speed, and therefore the force of the engine is equal to power divided by V, which is 50 kilowatts divided by speed of 25 meters per second, which is 2 kilonewtons, which is 2000 newtons. And the force, or the frictional force or the resistive force is minus that, minus 2000 newtons. Well, yes, it's backwards. The resistive force, the work done by the engine in 10 seconds. So B, work is force. Oh, no, it's power times time. It's power times time. And it's 50 kilowatts times 10 seconds, which is 500 kilojoules. That's it, 500 kilojoules. Next one. Water falls from a dam of height 15 meters at a rate of 500 kilograms per second. The efficiency of the generator is 80% by the electrical power output of the system. So we have water falling through a funnel. Let's take a picture. Hydroelectric dam. Mm. Right, so the water falls from a height. So the height difference is 15 meters. 15 meters. Water falls at a rate of 500 kilograms per second. So in time 1 second, the mass of the water is 500 kilograms. The efficiency of the generator eta is 80%, which is 0.8. And the electrical power, find the electrical power output. Power out. Okay. Well, we know that the power coming in is the work done by gravity. Gravity pulls down the water. So the water pulls down. So the work done by the gravity is mgh, as we already know. And power in, the input power is the power available from the water, is the work divided by time, which is mgh divided by time. And we know that the efficiency and see. Eta is power out divided by power in, which means that power out is efficiency multiplied by power in, which is eta multiplied by mgh over t. And now we can substitute. So 0.8 times mass, 500, times 10 times h, which is 15 meters, divided by the time, which is 1 second. And we get 0.8 times 500 times 10 times 15, 60,000 watts, which is 60 kilowatts. What is that? Well, it's the energy needed. You can boil 30 kettles at once. 30 kettles at once. Not that much if you think about it, but actually kettles use a lot of energy. Probably one of the hungriest device in your household, apart from the boiler, of course. Okay. Efficiency. If you have any questions, power is work divided by time. Efficiency is power out divided by power in. Right. Anyways, problem 8. A 0.2 kilograms object is attached to a vertical spring with spring constant K and is pulled down 0.1 meters. Okay, so if we do fit springs. Mhm. So if I take a spring and I pull it, you can see that I have elastic energy, and gravitational energy. And as I release, let's do no friction. So you can see that it's always a combination of the three: kinetic energy, potential energy, gravitational energy, and elastic energy. So when the spring is stretched, uh, the spring is stretched, it has elastic energy. When the spring is, yeah, so it's a, you can see how the transformations of energy take place. It's lots of stuff going on in here. Okay, so let's reset. So we pull down the mass and we release it. Okay. So let's say that this is the equilibrium position. equilibrium position. So the mass is here. So it's been pulled down by a distance of, so this is 200 grams. It's been pulled down by 0.1 meters. The spring constant is 250 newtons per meter. Attached to the vertical spring, it is reached from equilibrium. So the elastic potential energy stored in the spring is 1/2 k delta x squared. But also, when you pull it down from equilibrium, you are reducing the gravitational potential energy. So let's say the gravitational potential energy at this point is 0. Gravitational potential energy is 0 joules. And here, at this point, gravitational potential energy is mgh. Okay, so at the bottom, kinetic energy is 0, gravitational potential energy is 0, and the elastic potential energy is 1/2 k delta x squared, which is 1/2 times 250 times 0.1 squared, which is 125, 1.25 joules. Right. Now, when we release, so that's for question A. Elastic potential energy is this. B. The maximum speed of the object. So it will have a maximum speed at the equilibrium position. V is max at equilibrium. Equilibrium. Equilibrium is single L. At equilibrium. So at equilibrium, kinetic energy is 1/2 mv squared. Gravitational potential energy is mgh. And elastic potential energy is 0 because the spring is not stretched. It's in equilibrium. Well, technically it is stretched because it is stretched from the original position. But you can, the potential energy works in such a way that you can choose the position in which it is 0. Okay. So elastic potential energy is 0 in this position. So you can say it's the elastic potential energy from the not from the unstretched position, but from the equilibrium position. So potential energy is relative. That's an interesting fact. And therefore, we have elastic potential energy is 0. And now you can say that mgh, which is, what is that? 0.2 times 10 times 0.1, which is 0. So that's 0.2. 0.2 joules. Okay, and the kinetic energy, well, kinetic energy is 1/2 mv squared. But we know that the total energy must remain the same. Total energy. And therefore, 1/2 mv squared plus 0.2 joules must equal to 1.25 joules. And therefore, 1/2 mv squared must equal to 1.05 joules. And then mv squared equals 2.1 joule. V is equal to square root of 2.1 divided by 0.2, which is square root of 10.5. 10.5, yes, which is 3.24 meters per second. That's the maximum speed. All right. I think I'll leave you here, and I'll see you in 2 weeks' time for maths, for the next topic in maths. I don't remember which one it is, but enjoy, and see you in 2 weeks. Would it not be FV cos theta? Yeah, it would be cos theta. Yes. Thank you for that correction. But we assume a simple case where force is in the same direction as velocity.